Okay, hello grade 12s. Good morning. We're going to go over a review of unit number 4, and sometimes it's nice to go over all the concepts at the end because then you go back and refresh yourself of some of the most important things that we did at the very beginning of the unit. And because you didn't study for a unit test like we normally would, perhaps you didn't have a chance to actually consolidate that information and summarize it like you normally would. So let's take a few minutes and go over some of the highlights. So I've got 3 sort of groups of topics that I want to cover. The first 2 are going to take the most of our time. I want to go over Le Chatelier's principle, and I want to go over some of the sample calculations or the questions that we would do for Le Chatelier's principle. And then I want to spend a bit of time going over ice tables, okay? I had a few requests from you to do a few calculations together, so we're going to do that because how you set up an ice table and how you calculate a K value is going to be similar for what we start to do in unit number 5, which is our equilibrium part 2, our application of using equilibriums when we start having acids and bases together. Okay, so Le Chatelier's principle, right? When a stress is applied to an equilibrium system, the equilibrium is going to shift to reduce that stress, and a new equilibrium is going to be established. Now, a couple of things to remember. We're talking about a closed system. So that's like a container with a stopper on the top, if you think of it that way. You don't want to be having a system where anything can enter or exit once that equilibrium is established. Sure, if you're adding a stress to it, you may be increasing the pressure by decreasing the volume, or maybe you're adding in some concentration of one of the reactants or the products. But once you've added that stress, that system is closed, and then it will establish a new equilibrium. Okay, so there's a couple of types of stresses. We talk about those in terms of the concentration, right? Maybe it's something that you're increasing for the reactants or the products, and that'll depend on what happens to the system, which way it's going to shift based on whether the concentration you're talking about is a reactant or a product, right? Which side of the equilibrium symbol is it on? Addition or removal of heat. And what you need to think about in this case is that system an endothermic or exothermic? Like what side is the heat on? Because clearly if you increase the heat and it's on this side, it's going to shift it this way. If it's on this side, it's going to shift it this way. Okay? Also, you want to think about the change in volume. Now, the change in volume, though, is only going to affect if it's a state of matter that can be compressed. You can't compress a liquid and you can't compress a solid. So if you're changing the volume, you're not going to have any effect on the equilibrium simply because it can't be compressed. And remember, you're tying all of these stresses and you're tying them all to the molecular theory, right? The particle theory, because you want to be able to explain what happens at the molecular level. Okay, so what's happening to those particles? You just want to remember for the change in volume and pressure, those are linked. So if you're decreasing the volume, clearly you're increasing the pressure of a system. That would be this one right here. And if you're increasing the volume, you're decreasing the pressure. And we talked about the points from the molecular theory. Collisions, more successful collisions with the correct collision geometry with enough energy to be greater than or equal to the energy of activation, yada, 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 right? All of that explaining tone. There was one good graphic that I had that I think I posted. It's one of the compound chemistry ones. And I really liked it because it really goes into a nice summary for you. And if you can explain this graphic right here, then you really do understand equilibrium, okay? The concept that when a system reaches equilibrium, the rate of the forward direction is equal to the rate of the reverse direction. Once that rate is equal, then your system is at equilibrium, and the concentrations of the reactants in the products are no longer changing. It's still a dynamic system, but the rate that the reactants turn into products and the rate that the products turn into reactants, that's what's consistent, okay? There's always this graphic about shoveling dirt from one side to the other. And if you like that kind of a concept, then yeah, you can look at those analogies and get a bit more explanation for that. Basically, it's saying that 1 removes dirt at the same rate that 2 is replacing it. And when that happens, that's supposed to represent equilibrium because the rate would be the same. Then the size of the hole and the pile of the dirt is going to stay the same. So even though it's still changing, it's dynamic and it's happening at the same rate. And that is what an equilibrium is. Okay, so don't forget that. It's not static, it's still changing. But static in the terms only that the concentration will remain the same, but you're still moving dirt from one pile to the other, or reactants are still turning into products and products are still turning into reactants. Okay, what are the factors that affect it? Concentration, temperature, and pressure. All right, and that's a nice little summary right there. And you could do the same thing when you do yours. You could summarize all those stresses. Okay. So what do we want to do? I want to move on to the sample multiple choice test, and let's go over questions 20 to 28. So give me a second here and I'll skip all the way down to there. I want to explain those questions that were in the sample multiple choice test because those are a good little summary of all the stresses that can affect a system, and so let's have a look at those. Okay, so this was from the sample multiple choice test. Question number 20 to 28. Let's see if any of these changes are going to affect the equilibrium. All right, first one. We've got hydrogen peroxide here. We would do this one in the lab, right? Add a little bit of potassium iodide to the hydrogen peroxide. It decomposes at a faster rate. That's where you're going to collect your oxygen gas. Do you remember doing that demo? That's a classic one. So if you add a catalyst, does that affect the equilibrium? No, no change to the equilibrium, right? Because adding a catalyst just increases the rate at which the equilibrium is going to be established. It has nothing to do with changing or shifting the equilibrium. So that's the catalyst. Add that into your notes as a reminder. Next one is a concentration one. So we're talking about the removal of hydrogen bromide. Hydrogen bromide is on the reactant side. Remember, you're going to memorize that when it increases, it shifts to the other side. So when it decreases, it's going to shift this way, right? So if you're decreasing the concentration of this gas right here, it's going to shift to the left. All right, that's a concentration example. Next one is a temperature decrease. So if you've got a decrease in temperature, first thing you need to do is recognize is it endothermic or exothermic, and you might need to do a little bit of work here. What side is the heat on? Well, you know that if you have a solid and you have a liquid water, if you have an ice cube, that's your solid, you're certainly going to apply the heat to this side of the equation. So this is a change of state, a physical system, which of course can establish an equilibrium, okay? And it's an exothermic one, so if you decrease the temperature, it's going to shift it to the right, because if you increased it, it would shift it to the left. Okay, next one, temperature decrease again. This time, what side's your heat on? That is obviously the first thing you do again. So we've got solid sucrose and aqueous sucrose. So your heat is going to be on this side. Okay, oh, I'm on the wrong question, sorry. Heat is right here. And so if it's a decrease in heat, it's going to shift it to the left. Next one, temperature decrease again. Temperature decrease. Here's one where you've got to remember what's the general rule for dissolving salts. Dissolving salts are generally endothermic. This is sodium hydroxide. Sodium hydroxide is exothermic when it dissolves. So from going from a solid to aqueous, your heat is on the product side. Decreasing the temperature is going to shift it to the right. Next one, excess sodium hydroxide. Okay, this is a two-part question. You need to recognize that our sodium hydroxide is aqueous. When you think of sodium hydroxide and you see it as aqueous, you remember your net ionic formulas, and so you're thinking there are sodium ions there are hydroxide ions there. Is that going to bond with any of those ions that are available? Yes, it will. The hydroxide will bond to the hydrogen ion concentration. Therefore, the hydrogen ion concentration is going to decrease. If that concentration decreases, it's going to shift to the right. Okay, sorry if my left and rights are on the camera and backwards. I'll just go with what I'm saying. I'm doing the right the right shifting with my fingers if you were at my house in my own view. Okay, next one, temperature decrease again. We have a reflecting the enthalpy just as a positive value, and we learned that from last unit that is an endothermic reaction. That means my heat is on this side right here. So if I decrease it, it's going to shift to the left. Did I forget one? I did. The container volume decreasing with my N2O4 and my 2NO2. What's going to happen here? Okay, temperature, container volume decrease. Container volume decrease means increase in pressure. Those molecules are going to move faster and they're going to have more collisions, more successful collisions, and go from an area of high concentration to low concentration. So let's have a look at our molar ratios. I've got my big number here. It's going to go from high to low. It's going to shift to the left. I looked at the states and I recognize that this is a system that can be compressed. So for this system, because they're gases, you know that a change in pressure, because of the change in volume, will have an effect on the equilibrium system. Okay? An increase in pressure will always go from an area of high to low. So you've got to look at your coefficients to figure out which one it is. All right, here's the one below it. Same explanation. Let's figure this one out. Pressure decrease. Well, pressure decrease means increase in volume, okay? So let's look at our molar ratio. On this side, because we're all dealing with gases, I have 4 things in total. I've got 1 here and 3 here. That's 4. I've got 2 molecules on that side. If I increase the pressure, it would go high to low. If I decrease the pressure, it goes low to high. This will be a shift in equilibrium to the left. Okay, so that's our equilibrium review. Those are the stresses, and you always explain it by what's the stress. Here are your examples, right? Concentration, temperature, or pressure. What is the shift? Is it shifting it to the left or shifting it to the right? And what are the things that cause no shift? Well, if you're adding in a solid, that won't have an effect. If you're adding a catalyst, that's not going to shift the equilibrium. It's just going to increase the rate at which it takes place. So you're going to want to make yourself a nice little summary, if you haven't already, on stress, shift, result, and that idea of equilibrium. Okay? That leads us right into the next concept where we calculate the equilibrium constant. So for calculating the equilibrium constant, I want to go to the K value stuff, which is on page 21. So let's go back here. Do you remember that you had on the title page, there was a graphic that talked about equilibrium? You know, some people make like little cartoony graphics that have to do with summarizing a concept. Feel free to go back and look at that one now. Make your own that looks like that, because in that comic, there is an example of everything summarized. It summarizes Le Chatelier, it links it to K value, it links it to the Q value, and it also links it to the driving forces, which was the last part of our unit, right? Okay, so let me go back here and go to this concept of K. And again, this was on page 17. Okay. Calculating the K, what you want to remember here is that the K value is going to be the same even if you shift the equilibrium, because by shifting the equilibrium, it establishes a new equilibrium, and the only thing that's going to throw that ratio off is temperature. So temperature is the only thing that's going to vary the K value, okay? So if you calculate any K value, and again, it could be KC, it could be KEQ, this is our constant, okay? You have to remember that what you're putting into this equation is the concentrations at equilibrium, because it's the equilibrium constant. You're not just randomly calculating this equilibrium constant if you're not at equilibrium. That's where you get into that value of calculating a quotient. So let's use Q, for example, if you don't know if a system is at equilibrium, okay? Now, what values go in here? Only gases and aqueous phases. Solids and liquids aren't included in here. And that is one of the hardest things for you to figure out. They're not included because those concentrations are constant, because the concentration, if you think of it, of a solid or a liquid is really the density of that substance. So it's already factored in as something that is a constant already. And again, I'll encourage you to go back to page 439 in the textbook or see if you can summarize it as best you can. I summarized it as best as I could right here, but that's the hardest thing to think about. It just means that it's already factored in because concentration is density. So you're not changing the concentration, you're just adding more or less. And that's not going to affect the equilibrium, all right? Because then it's the surface area and it affects it both ways in the same rate. And so then it's kind of like adding a catalyst again, right? Like it doesn't shift the equilibrium constant, okay? So that's why when you're looking at the states in your expression, you only put in the values that are aqueous or gaseous state, okay? And it's always the concentration of the products over the concentration of the reactants. All right, let's show what that means again. I went over this in the module that we did with K, and I just wanted to make sure that I had this explained it right, because I know that there was, I re-listened to it, and I think I was sort of jumping ahead to the Q value. It just means that when you calculate a K value, mathematically you can figure it out if it's going to be a system that's at equilibrium that has more products or more reactants just based on the math that you calculate. Because if you're at a system where you have approximately the same concentrations of the products over the reactants, then you're going to mathematically come up with a value that's equal to about 1. So if K is close to 1, then it must mean at equilibrium, you've got about the same amount of reactant and product, because mathematically you divide them and you're going to end up with 1. If the K value is greater than 1, that simply means that you have more product than reactant, because you're going to have a bigger number on the numerator than you have on the denominator, and therefore you're going to have more product. And when we talk about equilibrium systems, we'll say it's favoring the products. Just means that at equilibrium, this is a system that has more product than reactant. And that is totally normal, right? You can have more of one than the other. That's what's hard to think about. People are always like, ooh, at equilibrium, it has to be the same. No way. It just means that the rate at which the reactants make the products and the products make the reactants is the same. The rate of change is the same, but you can have way more reactant than product, and you can have way more product than reactant. You can also have about the same. So when you put them into the K value, the constant just tells you this. And again, you go back to the title and the notes, right? The title tells it all. The relative size of the equilibrium constant tells you the extent of the reaction. Is it favoring the reactants or the products? That just means what you have more of. Okay? All right, now that we've established that, let's do, I know that we did an example here. I want to go over that Q value, and then I'll go back to doing an ICE table. Yeah, that's what I'm going to do. Okay, so the calculating of the Q value, which is the reaction quotient, is what you do if you're not sure if a system is at equilibrium. If you calculate Q and it comes up to being the exact same value as K, then yes, that system is at equilibrium. But you can figure out if the system is still going towards equilibrium, favoring a forward reaction, or if the Q value is favoring the reverse reaction, favoring the products. If you calculate Q and then compare it to K, so if Q is less than K, it means that it's still going in the forward direction. It's favoring the forward direction. It's favoring the products because it wants it to go in that way, or it's going in that way until it gets to equilibrium. Okay, so it's just a measured value to let you know where your system's at. And you'd be, of course, given that information, right? You'd be given the K value, you calculate the Q, and then it's like just figuring it out. If the Q is greater than the K, then it's still shifting towards the left until it reaches equilibrium, using the example it just happens to be right here. And if Q is greater than K, oh, same example down below. Okay, so that's why I summarized the K value and I summarize the Q value, and you would do the same, right? You summarize it to make it make sense for you. All right, now what we're going to do is I want to look at the sample problem. Let's do an ICE table, okay? I don't think I'm going to bother doing any more K calculations because I think that's fairly easy math. Go back and just do as many calculation questions as you need to set up for K, but that isn't too tricky. I think the ICE tables are trickier. So I'm going to do 2 ICE table calculations with you. The first one I'm going to do is from the sample multiple choice test. So let's go and look at that one. And you can cover up your solution and give it a try again. Then I'm going to go and do the ICE table that was in the quiz that I posted. Okay, so here we go. Question number 30 that is in the sample multiple choice test, and we're on page number 41. So let's see what this is and how you set it up. Okay. Given this equilibrium expression, here we go. We know what our reactants are, we know what our products are, and we're given what the equilibrium constant is. If the starting concentrations of the hydrogen gas is 1.6 mole per liter, perfect. I already know the initial concentration, ICE, right? Initial, change in concentration, and equilibrium. Those are the concentrations that we're going to put into our ICE table. Note also that you've got to figure out where your equilibrium symbol is. I'm not sure why it's that's a bit of a typo there. Your equilibrium expression symbol should be right here, right? Here are my reactants on the left-hand side, my hydrogen and iodide, and then they're going to the hydrogen iodide gas, okay? So it set it up for you a little bit by giving you some of the concentrations in the table, and of course you have to know where you're starting with. You're also starting with a concentration of the iodine gas as 1.60 moles per liter. And we also have some hydrogen iodide gas. We have 2.00 moles per liter. Now, in order to figure out which way it's going to change, you have to be given that information in the question. If you're given gases with concentrations, everything's there. The other questions we did were it's like there's none of the reactants and you're only starting with the hydrogen iodide gas, or you're only starting with the reactants of the hydrogen and the iodine gas and you don't have any hydrogen iodide. In that case, it's really easy to figure out which way the equilibrium is going. Is it proceeding in the forward direction or the reverse direction? If you don't have any of one of the gases, then you clearly can tell that. But if you're given all the gases, like in a question like this, well, then you need to be able to be told which way it's going. So we're told in the question that the reaction proceeds in the forward direction. In other words, the Q value isn't quite at K yet. The Q value, if you were to calculate the Q value based on those concentrations, because if you didn't know if it was at equilibrium, you could do that, and you would find that the Q value would be less than K. K is 9, Q would be less than 9. You could also then not be told whether it was the forward or the reverse direction if you were just given the Q value. Could you do that then? Okay, so you've got to pick up that information from the question. Which way is it going? Once I know that, I'm going to look at my change in concentration. So I need to figure out the equilibrium concentration of my hydrogen iodide gas. So I'm going to let X be the change in the concentration of the hydrogen gas to reach equilibrium. Okay, so I know it's going to the right. So therefore my change in hydrogen iodide gas is, or hydrogen gas is going to be negative X. It's going to go down by a factor of 1X. Where did that 1X come from? The coefficient, because they're going to go in molar ratios, right? I have 1, 1, to 2 ratio. So everything on the reactant side is going to go down by a factor of 1 for the hydrogen, also 1 for the iodine, but now look at your hydrogen iodide gas. It's going to go up. I know that concentration is going up because it's proceeding in the forward direction still. So it's going to go up plus by a factor of 2x. Okay, so now my equilibrium concentrations, I can write those in, then come up with my K and solve for those concentrations. So here we go. At equilibrium, it will be 1.60 take away X, 1.60 take away X, 2.00 plus 2X, okay? My K expression. So my hydrogen iodide gas is my products. I square it because there's a coefficient of 2. The coefficient becomes the exponent all over the concentration of my H2 gas and my I2 gas. Okay, hopefully I've got enough room to do it over here. Now I know what my K value is, so I'm going to solve it. I'm going to plug that value in right now. I'm going to go ahead and do my basic algebra. And again, I always say that feel free to do your algebra however you like to do your algebra. I notice that if I've got squares on both sides or squared exponents, I'm going to do the square root for both sides. So square root this side, square root this side, and I'm going to be left with 3.0 equals 2.00 plus 2x over 1.60 minus x, and again I bring it up, so I've got 3.0 times 1.60 minus x equals 2.00 plus 2x. So follow it down. Do you get to 5x equals 2.8 and x equals 0.56? Once I know what my x value is, I'm going to plug it in, and solve for my concentration of my hydrogen gas, which is the same, as the concentration of the iodine gas, and that is 1.60 take away 0.56, and at equilibrium, those gases will have a concentration of 1.04 moles per liter, and plug it into your hydrogen. That's really messy, your hydrogen iodide concentration, and you're going to end up getting 2.0 plus 2 times 0.56 and end up with 3.12 moles per liter. That is calculating my equilibrium concentrations of those gases, and I can solve that because I'm given K. Yeah, have to be given something in order for you to solve that equation. Okay, are you ready to try the one that was on the quiz? Okay. Sorry that when I set up the quiz question, I thought it was going to be easy to do both of the two, like kind of separate them out, and it wasn't as easy as I thought. So I would have done it as two separate. I thought it would be able to mark the first question and the second question separately, but in case you had to get both of them right in order to get the full mark. Okay, so in an experiment, 1.2 moles of SCH4UI gas are injected into an empty 2-liter container. Ooh, that was the trick in this question. You had to recognize that your concentration moles per liter then would be 1.2 divided by 2 to give you 0.60 moles per liter. Okay, after equilibrium was established, 1 mole is found in the container. So what concentration is that it's saying? Well, that refers to the fact that you've got I guess let me just make that a little smaller for a second. Okay, 1.0 divided by 2.0 equals 0.5. Okay, so what are the equilibrium concentrations? Let's fill in our ICE table. Initial concentration, change in concentration, equilibrium concentration. If 0.60 goes to 0.5, my change in concentration is by a factor of X. It goes down by a factor of X. What were my initial concentrations here and here? They were 0. Clearly they're going to go up, right? You didn't have any to begin with, and at the end you're going to have some. So all of the things that are on the reactant side are going to increase. This is going to increase by a factor of X. This is going to increase by a factor of 2x. Okay, so this will be x, this will be 2x, and then we've got our factor, or we already know our equilibrium concentration for your final product. So 0.60 take away x equals 0.5, x equals 0.1. Therefore, the concentration of our CO equals 0.1, and our concentration of our H2 is 2x equals 0.2. So the answer for the first one was D, our equilibrium concentrations for the two gases. What would be the value for K? Now that you know your equilibrium concentrations, you set up your K expression. K equals CH3OH over the concentrations of your reactants. Oh, that is just our H2 to the exponent 2. Plug your numbers in. 0.5 over 0.1 times 0.2 squared, and your K value was 125. Okay, so the answer for the second part was 125 for my Ke, which is the equilibrium constant, and you can calculate a constant if you're using the concentrations at equilibrium. Okay, and that's your ICE table. So you do want to practice that. I know there are lots and lots of questions in your notes about that. Go back again and try that. Make sure you can get it, because oftentimes it's the hardest part is figuring out what your change is going to be. But once you realize which one's going up and which one's going down, sometimes that is the only thing you need in order to help you solve those questions. Okay. Lastly, what do I want to go over is I just want to go over that concept of driving forces, okay? So the driving forces, again, what's going to push a system to either go to completion or favor the reactants or favor an equilibrium just has to do with what wants to push that system in the way that the natural forces of the world want it to go. So minimum enthalpy, maximum entropy. Minimum enthalpy means that the exothermic direction is always favored. Maximum entropy means that whatever side of the equation has the most disorder, the most randomness, right? The randomness property is the one that's going to be favored. So you just look at to see what the states are to talk about which one is favored with more disorder, okay? And then you look at what's factoring or what's the push between both of these. So let's look at question number 4. If you have a system here that has minimum enthalpy, maximum entropy, which way are they favored? If the minimum enthalpy is favoring the exothermic direction, it's favoring towards the products, favors the products, favors the right towards that direction. Remember the terminology, there's lots of different ways to say that. Maximum entropy favors the reactants. And so if one force pushes one way, the other force pushes the other way, you're going to get a system that is stuck in equilibrium because it wants to go both ways. And those are the forces that we say drive them that way. Okay. Yeah, I'm just going to move on because that basically, helps you determine whether it's going to go to system. But you can still have a system where both of them are favored towards the right or both are favored to the left. You can still have that, right? It just means that it still sets up an equilibrium because of the state that they're in, and that's most stable for them. Okay, so that was looking at that, and I think that was it for the equilibrium and then our driving forces. Okay, so the only thing I would do would be go back to your unit title page, and if you have a look at the cartoon that is on the very front page, it explains the entire unit all in one graphic. You've explained Le Chatelier's principle. You've talked about how to make a happy system, what makes it equilibrium, okay? What are the stresses that can cause a shift to the equilibrium, make it not happy, and then your equilibrium will be established again? How can you figure that out by calculating the K? The fact that temperature is the only thing that can change the K value. Everything else, the factors stay the same. So it's just you could calculate and get the same K value. How do you know if your reaction is at equilibrium or not? You can calculate a quotient, the Q value. If it's less than K, it's still going in the forward direction. If it's bigger than K, it's going favoring the reverse direction. And then it talks a little bit more about free energy, Gibbs free energy, and what are the driving forces. Okay, so that was a lot, and I hope that was helpful. If there are any other particular questions you want me to go over, we can do that. And I think what I'll try next time to do is do a little video at the end of unit number 5 where I explain some of those calculations. And I know that a few of you really want me to do a few more calculation explanations, so I'll try to do that. Even though it's taking me forever to upload some of the videos because of the length of them, but I'll try as best I can to give you a bit more, especially when we calculate K for our acids and our bases. Okay, I hope that was helpful, everybody, and I hope you're doing well. We'll talk to you next time.